A lot of functions grow really big, but some functions grow big faster than other functions. And in this video, we're going to talk about what I sometimes call the Big Theorem of limits, which is this hierarchy of how fast different functions grow. All of these functions actually become enormous when their inputs are large. Logarithm, for instance, of a really big number is a really big number. But a polynomial like n squared grows faster than logarithms. Exponentials grow faster than polynomials. Factorials, which take an integer input, which is why I've written all of these as n's and not x's, grow even faster than exponentials. And finally, n to the power of n is beating out everything else on this list. So in this video, we're going to talk about what do I exactly mean by this big theorem of limits. We're going to visualize it. We're going to see how we can use it in actual computations of different limit problems. And then finally, we're going to prove these statements so that we can be convinced that in fact, this relationship holds. To get a sense for how fast these different functions are actually growing graphically, let's turn to MapleLearn. MapleLearn is actually the sponsor for today's video and creates a wonderful web application for being able to compute mathematics, make mathematical documents, and most important for our purposes, to visualize mathematics. Let's begin with the function, the logarithm of x. Logarithm is a function that definitely grows as the inputs get larger, the outputs get larger as well. But it actually grows much, much smaller than other functions, like, for example, just x squared. And you can see here that when I plot both on the same plot, x squared as a polynomial just grows so much faster than logarithm, such that you can barely see the value of logarithm on a plot, even at x equal to 10, where the polynomial has gotten pretty large. So polynomials beat out logarithms. Okay, let's add the next one. Let's do e to the x, for example, here. And yet again, the green logarithm is almost completely gone from the graph. And this exponential itself, it also completely dominates the polynomial. The polynomial is almost invisible at the value of only x equal to 10 in comparison to how large, looking like some number in the tens of thousands, that the exponential is. It just grows so much faster. And let's just go all the way to the big guns. Let's go x to the power of x here and look at how that y-axis automatically formulates itself. As you hit values like x equal to 12, or what does that look like? Something in the order of magnitude of 10 to the power of 15. This function grows so dominatingly that you can't tell that even the next biggest function, exponentials, which you probably think exponentials are pretty good, it makes exponentials look horizontal. That is the dominance of this particular function. All right, so at least graphically, we've seen some motivation behind this hierarchy. Now, I do want to mention that the two numbers in there, the n squared and the e to the n, those numbers are kind of arbitrary. You can replace them with arbitrary a's and b's. Instead of n squared, I'll just put n to the a, where a is greater than 0. That just means some polynomial. And instead of e to the n, I'll put b to the n, so a generic exponent where the b is greater than 1. Now, what this kind of funky symbol means, this sort of like double less than symbol, it means that the thing on the right is far greater than the thing on the left. And specifically what that means is that if you take the ratio of those two things, their limit is going to be 0. That is, the first inequality that we have is just the same statement as saying that the limit is n goes to infinity. So for really large inputs, that ratio of the logarithm divided by the generic polynomial n to the a is just 0. And this just basically tells us that the denominator completely dominates the numerator. Likewise, for the fact that exponentials are better than polynomials, we'll have a different limit here. We'll say that the limit is n goes to infinity of the generic polynomial divided by the generic exponential. That will always be 0 for any values of a and b that fit these conditions. Thirdly, we're going to say that the ratio of the exponentials to the factorials is going to go to 0. And finally, the ratio of the factorials to the n's are going to go to 0. That is, to prove this hierarchy, I have 4 different limits that I have to show you. Now, before I go to those proofs, I want to show how I might use this hierarchy. Like, how can I actually use it to solve problems? And for that, I'm going to remind you of a pretty standard problem from first year calculus. The idea of the limit as n goes to infinity of a rational function. So this isn't using the hierarchy yet. It's just a polynomial on the top and a polynomial on the bottom. And I'll remind you that the method to solve a limit like this was You just found the highest power on the top and the bottom, which in this case is n to the fourth on the top and the bottom. And the idea is that the n squareds, the n cubes, the -1, all of that is irrelevant. It's irrelevant when n goes to infinity because the n to the fourth just utterly dominates. So I can look at this and glance at it and say that the answer is just going to be 1/3 because the coefficients of n to the fourth are 1 on the top and 3 on the bottom. To be slightly more rigorous than this, maybe I will just pull out an n to the fourth on the top and the bottom. And if I do that, I can clearly cancel the n to the fourth on the top and the bottom, but then all those other expressions like 2 over n squared, all of those just go to 0 as n gets large. So the only thing remaining, the only thing that doesn't get canceled or doesn't go to 0 is the 1 on the top and the 3 on the bottom, so 1/3. The final answer to this limit is 1/3. And you can use the same basic idea for any of these rational functions. This one, for example, is one where it's n to the fifth on the top and n to the fourth on the bottom. The n to the fifth on the top dominates, and as a result, this is just going to go to infinity. There's more n's in the numerator which are getting large. And conversely, in this example, where the n to the fifth, the biggest thing is on the bottom, the denominator's power is higher than the numerator's, the denominator drags it down and it's just going to be equal to 0. So this is, again, a classic first-year calculus problem, but what I'm going to add with this big theorem is now we can do limits like this one that combines n to the n's and n factorials and n to the 100s. And you might look at that n to the 100 and you're like, that looks enormous because 100 is a big number. But it's always much, much smaller than exponentials or factorials or n to the n's. Indeed, if I look at this and try to figure out what's the highest term on the top, highest term on the bottom, well, both of them are n to the n terms. Even though n factorial is enormous, it's irrelevant compared to n to the n. Even though n to the 100 is enormous, it's irrelevant compared to n to the n. I can do the exact same trick to show this formally. I'm going to factor out the n to the n, and you just get two terms which are going to cancel out the front, and then a whole bunch of other terms whose limits are all 0. That was the point of our hierarchy, that things like n to the factorial over n to the n, all of those are going to be 0. So what's left? The 1 and the 3, and again, this one is equal to 1/3 as well. Now, if you ever want to check the results of your limit computations or get a quick answer, you can always go to what is my favorite calculator on the App Store, the Maple Calculator. The same people who make the Maple Learn I talked about earlier on in this video. So if I go here and I go to the Maple Calculator, I can put in limits like this. So I'm going to go and write the limit. X is going to infinity. And what one should I do? Well, let's do something kind of similar. X to the power of x, and then I will divide that out by, I don't know, x to the power of x. What else should we add? Maybe an exponential of x, and I don't know, what else should we do? How about an x to the power of 100? Using what we've learned, we can say x to the x on the top, x to the x on the bottom. Those are the dominant terms. Everything else is irrelevant. It should be 1. Let's go and check it. I'll hit the check button. And indeed, the Maple Calculator confirms that this limit is equal to 1. And the Maple Calculator is just so useful for being able to do that quick verification of limits to make sure that you're on the right track. So I definitely encourage you to check out the links down in the description. Okay, now that we've seen how we might use this hierarchy of functions, why is it true? That is, we have these 4 different limits, and we basically need to argue why each of those limits is true. And there's some kind of interesting proofs that we get to see along the way. I want to begin with my favorite of them, which is the final one. The limit as n goes to infinity of n factorial divided by n to the n. And the claim is that this is equal to 0. Well, why is that? Now, if I go and write out these two things, okay, so n to the n is just n times n times n times n times. There's n copies of n times n times n times n. Then n factorial is like 1 times 2 times 3 times 4, all the way up to n minus 1, and finally up to times n. So in both of these cases, there's n factors, but they're slightly different. So now if I take the ratio of these things, n factorial divided by n to the n, you can see how they kind of line up. 1 over n, 2 over n, 3 over n, and so forth. And my claim here is that this is going to equal 0. Now, certainly the denominator is bigger than the top. I mean, you can just look at, just say the first term and see the 1 over n. But just because it's bigger on the top than the bottom doesn't necessarily mean that it's going to go to 0, although we might guess that that's the case. So we still have to do some work to prove that. And what I'm going to do is I'm going to factor out that first term, the 1 over n, and then I have a whole bunch of other stuff. Now, as n gets big, the things inside of the bracket, each individual factor gets small, like 2 over n gets small, but then you're multiplying by a whole bunch of them. What exactly is the limit? Well, the easiest way to deal with this is to say that everything in the brackets is clearly less than 1. So this is just less than 1 over n. I know what the limit of 1 over n is. The limit of 1 over n is just 0, and so the limit of n factorial divided by n to the n by the squeeze theorem is just equal to 0 as well. Okay, what about some of the other ones? Well, let's take this one, logarithm of n divided by n to the a. So these are the polynomials, like n squared is an example of an a. Now, to do this one, we're actually going to use L'Hopital's rule. L'Hopital's rule says if you have an indeterminate on the top and the bottom, like this kind of generically looks like an infinity over infinity, if you just naively plug in n equal to infinity here. Well, that's an indeterminate form, and so what we can do is we can take the derivative of the top and the derivative of the bottom. That is how L'Hopital's rule works. So if I take the derivative of logarithm of n, I get 1 over n. If I take the derivative of like n squared, it would be like 2n to the 1. So in general, n to the a is an to the a minus 1. Well, the 1 over n on the top can just be brought down on the bottom, so now it's just an to the a on the bottom here. And everything is now on the bottom, so that's clearly getting large as n goes to infinity. This is just equal to 0. So this limit just falls immediately via L'Hopital's rule. And in fact, L'Hopital's rule is also the solution to the next limit. I'll let you fill in the details for this one. It's a bit of an exercise. You've got a polynomial on the top, say it's n to the 100. Well then, 100 applications of L'Hopital's rule would eventually take that numerator down to just a constant. Everything else would remain on the bottom because exponentials never go away when you take derivatives of them. And so you just have everything on the bottom, a constant on the top, it would go to 0 as well by L'Hopital's rule applied as many times as you might need. Okay, and then the final one, the final interesting one that I find is the limit as n goes to infinity of b to the n over n factorial. Okay, so how can we deal with that? And in fact, we get to use another very powerful theorem from calculus to solve this one. So what I'm going to do is, just to make my notation easier, set up the name of a sequence that I will call a sub n. And that's just going to be the terms that I want to talk about, the b to the power of n divided by the n factorial. This is just a shorthand. Now, what I want to note is that if I take a n plus 1, like the next term in the sequence, so everywhere there's an n, I'm going to plug in an n plus 1, so I'm going to have a b to the n plus 1 divided by n plus 1 factorial. If I do this, I can actually factor out some stuff. On the top, let me factor out one copy of b. On the bottom, n plus 1 factorial is like n plus 1 times n minus 1 times n minus 2 and all the way down. I'm just going to pull out the n plus 1. And then that leaves me with n plus 1 times n factorial. And then when I look at this, I have some yellow stuff stuck out the front, but everything else I recognize, that's just my original sequence an. So in other words, what I've said is that an plus 1 is equal to b over n plus 1 times this an. So we get this sort of recurrence relation for this sequence. Okay, so fine, but what can I do with this? Well, I want to note a few things. The first thing is, now I know that this sequence an is eventually decreasing. What I mean by this is that because the only thing that's changing here is that n out the front, and as n gets larger and larger and larger, first of all, eventually n plus 1 gets bigger than b. That's why I say it's eventually decreasing. But then as time goes on, you're just always multiplying by numbers that are less than 1, less than 1, less than 1. So your sequence is just getting smaller and smaller and smaller, at least eventually. Okay, so it's decreasing, great. The other thing I'll note is that it's bounded below, and what I just mean by this is that every term in this sequence is positive, right? There's nothing that's negative here. B is a positive number, and if it starts positive, then everything will be positive. What you have is a sequence that's going down, 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 but can't go down to like negative infinity because it's got this bounded below at 0. So it's going down, 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 down. It has to settle somewhere. This is the monotone convergence theorem. And so it's saying that this sequence an has to have a limit. It has to have a limit by the monotone convergence theorem, or sometimes the monotone sequence theorem. I'll put up a link to a video of mine talking about this theorem in more detail, but the point is it has to have a limit. I actually don't yet know that the limit is 0. I just know that it has a limit. So given that it has a limit, let's go and try to do a computation to find out what that limit is. Well, I can use the same basic formula. So I got the same recurrence relation. Let me take the limit as n goes to infinity in front of both sides. On the right-hand side here, it's a product of two things. So I can separate that out and say it's the limit of the b over n plus 1 and then the limit of the an. Now, if the sequence an goes to L, the sequence an plus 1, it also goes to L. It's just like one term further, getting closer to that limit. So on the left-hand side, if the sequence goes to a limit L, then it does as well. The limit of b over n plus 1 is clearly just 0, and then the an's is an L again. So I've got L is 0 times L. L better be equal to 0. And note carefully, this argument only works because we knew that it had a limit. If we hadn't done the earlier proof and used the monotone convergence theorem, you wouldn't know that this had a limit, even if you deduced that if it had a limit, it would have to be equal to 0. So we found it does have a limit, and that limit is equal to 0. And so we've deduced the final one of our 4 limits that we need to do, thus establishing the big theorem of limits, this hierarchy of functions. All right, if you have any questions about this video, please leave them down in the comments. Definitely check out the Maple calculator for your phone or Maple Learn for the browser, and we're gonna do some more math in the next video.